Welcome to the Silicon Labs webinar. It's covering the Internet Infrastructure Design Challenges. The purpose of the webinar is to share solutions to some of the most common challenges facing engineers like yourselves today when you're working on equipment for the Internet infrastructure. A design challenge that is really common right now is created by the various high-speed standard interfaces that you guys are faced in your designs. Altera is a solution found at the heart of many of these, trying to integrate all these different standard protocols. Min will discuss how the Stratix family helps customers, and then Len, you'll introduce how Silicon Labs solutions are complementary to that. I think this slide is a good way to introduce Min and the Altera solution, but I wanted to highlight that on the left, it shows all the different timing requirements. Design engineers today are seeing these in their typical designs. It shows possibly a PCIe switch or several Ethernet standards, whether it's 10 gig or gig PHYs that are in the design. These devices all require different clock frequencies, anywhere from 100 to 156.25 megahertz. In addition, some of the designs, as you can see here, will have different clocks for a control processor or the memory or the high-speed mezzanine cards. With all of these together, the design engineers are looking at a lot of different clock requirements. That is the basis of the challenge that we're going to try to talk to you guys about today. What solutions can Altera and Silicon Labs suggest for you guys to help you with these requirements? Min, can you discuss just a little bit about how customers can leverage Altera's Stratix family to tackle integrating all of these different standard protocols?
Sure. Thanks, Kyle. Moving on to the next slide. So as Kyle presented, there's a bunch of challenges when it comes to delivering the bandwidth needs of both data centers and the IoT applications. So one of the challenges we face with just trying to address all these issues is sort of the bandwidth. And how do we address this with Altera FPGAs? So Altera has the Stratix series family, which caters to the bandwidth needs of these applications. So here we're looking at the Stratix 5 GT family, and with the number of transceivers available for Stratix 5, we have 32 GX transceiver channels capable of 14.1 gigabits per second. And for the high-speed bandwidth, we have the GT transceiver channels, which are capable of 28 gigabits per second. So on this slide, this is showing the internal clocking network of the reference clock network. So this is where Silicon Labs can play a big part in addressing the various reference clock requirements. So the reference clock network is used to distribute the PLL reference clock. The Stratix family has three possible reference clock sources. The first is a dedicated reference clock pins. The second is any unused RX pins. And lastly, from an FPLL internal to the device. The reference clock network then drives directly into the PLL. There's also a dedicated feedback clock path for the PLL feedback bonding. So now I'm going to hand it back to Kyle.
Oh, well, thanks, Min. So it is important for the customers to take advantage of these different reference clock inputs. But when we turn it over to Len, why don't you talk about how Silicon Labs has a solution that helps the Altera FPGA?
Thanks, Min. Thanks, Kyle. So Altera and our partnership really wants to make sure that we bring out the best in Altera technology. And really, as Kyle mentioned earlier, there are a lot of different frequencies, a lot of different standards that have to be supported in this market whether you're supporting Internet of Things, the Internet infrastructure, everything from USB to high-speed Ethernet or to different frequencies for optical networking. And because Altera's solutions are so powerful, in order to deliver those solutions, many different frequencies have to be supported. And not only within just the Altera FPGA with very demanding specifications, but also other things that are happening on the board. And in this slide, we're pointing out really may look familiar to your application where you have a lot of reference clocks, like the one that Min was talking about, and also data plane clocks with really high-speed SerDes. It could be Ethernet. These frequencies may look familiar to you, but you probably have some sort of a SerDes application where you're bringing in a very fast stream of bits. You want to keep the bit error rate low, yet you're still really, the PCB still demands a lot of different frequencies to support them. And so what happens in order to hit all those different frequencies for all those different standards, hit the phase noise requirements for all of those specifications, and to drive things like the PHYs if those phase noise requirements are very, very stringent, making it very difficult to hit all of those frequencies and specifications that are required across that board with all those chip suppliers, and not have it blow up into a very large, what we call a clock tree, where you have to use multiple dedicated local oscillators that can be very expensive, fan-out buffers, and other clocks, which will synthesize a lot of different frequencies for you. What Silicon Labs tries to do, and in our partnership with Altera, why I believe that we work very well together, is we're very good at developing technology that with a single chip or with fewer chips, you can actually hit all those different frequencies, whatever they are, from PCB to one application to another. Be able to hit all of those and still hit all the phase noise requirements, all of the jitter requirements, all of the accuracy requirements that are demanded to keep to really take advantage of the high performance that you would work with, for example, in a Stratix 5 FPGA. You don't want to spend a lot of money on that and then not get the performance that you could in your end application. So you can see on the left-hand side in the conventional approach, often customers are resorting to a lot of different clocks and a lot of different timing components to hit all those specs and frequencies, where Silicon Laboratories' multi-synth technology in our clock generators deliver best-in-class phase jitter and can still produce all the frequencies that you need. So how do we do that? One piece of technology and IP that we've developed at Silicon Laboratories is Multisense. At a very big picture level, what happens is often when you have to generate a lot of different frequencies, you really have to mess up the clock. And Altera wouldn't appreciate that if we were heading in a high jitter reference frequency or data plane frequency for SerDes and really mess up the clock because we had a lot of different frequencies that we needed to provide for you. So this is what Multisense does for you. Multisense in most products you would think of as just a fractional divider. So that's pretty simple, right? You're just dividing. But when you have to divide and resynthesize a frequency like that, a clock, you might not always pick the right edge, and you'll introduce two things. You'll introduce more phase jitter or phase noise, and you'll introduce some accuracy error because you're not going to get quite the right edge on every clock. So that's in the conventional approach. The Silicon Labs approach is to use what we call as an interpolative divider. It actually has a fractional end divider like you're used to using, but there is a phase error detector and an adjustment. And so this is maybe an oversimplification of what this IP really is, but what it delivers is 0 ppm error for any frequency that's coming in, still based off of the 1 PLL. And so what really that does for you is it gives you any frequency, and we don't mess up the clock as much as other suppliers. We still keep that phase jitter very, very low, whereas if you look at the fractional phase jitter in most data sheets for different timing products, you'll find out that when you got to do fractional stuff or odd frequencies, it really messes up the phase noise. So then you have to resort to many different devices. And really, the real-world application of that is that you can then use just a single chip and hit all of the frequencies that you need and still hit all of the specifications that you need.